Ooh, a 9-liter tank at 16.4 degrees Celsius is filled with 15.8 grams of dinitrogen difluoride gas. So that's N2F2. And 2.60 grams of chlorine pentafluoride gas. You assume both gases behave as ideal gases under these conditions. Calculate the mole fraction and partial pressure of each gas and the total pressure of the tank. And then we need to round our answers to 3 significant digits. So the easiest part here we're going to actually tackle is the mole fraction, because we're going to convert those grams as they listed into moles. So dinitrogen difluoride gas, okay, will be written as I said, N2F2, okay? And chlorine pentafluoride is known as ClF5, because penta 5, okay? Now, let's write down also in the information. We have 15.8 grams and 2.60 grams, okay? And we know it's a 9-liter tank. And we know right now the temperature is 16.4 degrees Celsius, okay? So, that is all the information that they've given us. So now let's go through. First thing I want to do, we won't need it now, but just because we are going to use our PV equals nRT formula, the temperature there works in Kelvin. So we have now 273.15 plus that 16.4. So we actually have 289.55 Kelvin. Let's leave that there for now. First thing we're going to do is solve for the moles of each one. N2F2, we need to go to our periodic table to find its molar mass. Nitrogen, there's 2 of them, and the fluorine, there's 2 of them. So that's 14.007 times 2 plus 18.998 times 2. That's dinitrogen difluoride, 66.01 grams per mole. Okay, and the ClF5, okay, so that's chlorine, so that's 1 chlorine, so 35.45, okay, plus F5, 18.998 times 5, 130.44 grams per mole. Okay, and just double check we have it. Dinitrogen difluoride, perfect, and chlorine pentafluoride. Okay, so now we're going to find the amount of moles. That's why it's important to always have units, because in order to convert this from grams to moles, we'd actually divide by the molar mass, so that way the moles would be now at the numerator and the grams get canceled out. So that's 15.8 divided by 66.01. Okay, and we get 0.239, etc. Okay, I'm not going to round just yet because they asked for the mole fraction, and I want to get the most accurate numbers to get that mole fraction. Okay, and now we have 2.60 divided by 130.44. It's going to be quite small, and we do get 0.0199. So the way you calculate molar fraction, okay, and partial pressure of each gas is that you want to have the moles over the total moles. The moles of that gas over the total moles. So we're going to add these two together, the 239, etc., and the 0.199, etc., and we get total is 0.259, etc. Okay, and now we want to divide. So for N2F2, that gas, the molar fraction is going to be, so 3 significant digits. We have 0.239, etc., divided by 0.259, etc., and we get 3 sig digs. Okay, that would be 92.3. The reason why we have 92.3 is because we have to multiply by 100 to get, I guess, that'll be more percentage. I'm going to leave it actually as a decimal to emphasize a fraction. So 0.923. That'll be the molar fraction there. And now for the other one, okay, we're going to have 0.199 divided by that total we found, and we get, for 3 sig digs, 0.0769. That would be 3 significant digits for that one. So now we found both gases, okay? Alright, so now just to make sure we're not missing anything, we want now the partial pressure of each gas. So what they're asking us to do is find for each one what the P is in the formula PV equals nRT, okay? So that would actually be P is equal to nRT over volume, okay? And so I'm going to actually solve an ATM, and if we actually go over to our units, hopefully it will be there. We want to find out the R value. Actually might be in the physics one, but let's just check this one first. As soon as it loads, and we're actually going to load this physics one as well. So we have units of energy, units of pressure, perfect. ATM, these are just conversions, so hopefully it's here as our formula. Let's see here. Oh no, wait, we just wanted the R value, okay? And we do not have it. Gas constant R, perfect. This is one we'll be using here, the 0.0820575, just so we can get the ATM, okay? We're not, because we're given liters, and we're given the mole, we're given the Kelvin. We're not using the ones with the joules, okay? So with that being said, we have, for each one, it's going to be N, okay? So we're not using the mole fraction, we're actually going to use the actual mole number, which is the 0.239, okay? For the N2F2. So that times the 0.0820575, just to make sure I have that correct. Yep. And now we're going to multiply that by the temperature, which is going to be 289.55. I'm going to divide that by the liters, and the liters, as we discussed, was 9. Okay? And we get, for this one, the pressure is going to be 0.6332. Okay? That's what we're going to get. Alright? And we can actually put ATM as a unit. Okay? Because the mole fraction doesn't really have a unit because it's just moles over moles, so it just cancels out. So that'll be for that one. So now for the smaller one, we have now same thing, that times, let me just make sure so I don't mess anything up. Okay. Times everything else that we just did, and we get for this one 0.0526 partial ATM, atmospheric pressure, okay? And now for this one, the last part is going to ask for the total pressure of the tank. For this, actually, if we just follow the laws, we actually just do P1 plus P2, okay? And so the total pressure actually that you'd find when you add these two together would actually be 0.685 ATM. And the cool thing about doing it like that is that you could have also just gone with the total moles for this, and actually you would have still gotten around the same, if not exactly the same answer. So this times everything that we did up here. Okay, let's see. Okay, we get 0.685. So just as a review, we found our our mole fractions here for N2F2 and ClF5. We found out the atmospheric pressure for each partial pressure, and then we found the total pressure, and we rounded each to 3 significant digits. Technically, As you'll see in the answer, they did round 3 and 2 just to make sure that they ended around the same. Just want it to be as accurate as possible. So with that being said, as we go through this question, yep, the mole fraction, they did get 0.923 and 0.077, which is pretty much what I got if you round it just a little bit. Same thing here, 0.634. The reason why the number is different from mine is only because at this point they are using rounded numbers. As you can see, they use the 0.24 moles, and the same thing here, they use the 0.02 moles, while I kept with the most accurate number. And so that's why the numbers vary slightly. And what they did here, the total pressure, as we could do as well, P1 plus P2, that's how they got 0.687, and that's how I got 0.685. Nonetheless, this is correct. The one thing I would like to stress though is that just like whether it's with math and everything else, you want to save your rounding till the last part as much as possible. I know sometimes numbers do get big. That's why we make sure that we try to go as far as possible. Well, still as far as comfortably possible. You don't want to overdo it, but at the same time, you don't want to be cutting off your numbers too early, because that way you want to get the most accurate result. Okay? So question number 14. Okay.